This is problem number 31 on page 67 of chapter 3. The problem reads, a projectile is shot from the edge of a cliff, 125 meters above the ground level with an initial speed of 65 meters per second at an angle of 37 degrees with the horizontal, as shown in the figure. The first question is, determine the time taken to hit point P on the ground. I've copied the sketch here so that we can talk about it. Let's recognize that our final Y position is down here on the ground and our initial Y position is up here on the top of the cliff. Therefore, because of the difference between these 2 points, our delta Y is not equal to 0, so we can't use the range equation. It's also not horizontally fired, which means it falls into this kind of last class of projectile problem. I'm going to go ahead and start this problem as I would all my projectile problems. I'm going to separate everything that's happening horizontally from everything that's happening vertically in the problem so that I don't really make any mistakes or moving stuff that's in the x-plane over into the y-plane. I'll go ahead and start by writing the first equation of kinematics. Y final is equal to y initial plus my initial y component of velocity times time plus 1/2 at squared. Right out of the gate, you should recognize, as you should in most of these problems, that the initial y velocity is the initial velocity is the y component of velocity. So I should recognize that I'm going to have to basically resolve the vector into its x and y components. So therefore, I can say that the y component of the vector is going to be equal to v sine theta, or in this case, 65 meters per second times the sine of 37 degrees, and that gives me something on the order of 39.1 meters per second. I've run out of space for units there. In the x direction, I can say that the x component, I might as well do it while I've started, is going to be equal to the magnitude of the velocity vector v times the cosine of the angle. So I'm going to get 65 meters per second times the cosine of 37 degrees, and I'm going to get 51.9 meters per second. Again, I've kind of run out of space. Okay, now I'm going to continue this problem. I'll move a little bit further down and I'll plug some things in. My final velocity is going to be equal to 0, and my initial velocity is going to be equal to positive 100 and, sorry, not my initial velocity, my initial position, 125 meters. I'm going to add to that my initial velocity in the y direction, which is going to be 39.1 meters per second. And I need to multiply that by t, and I'm going to add 1/2 my acceleration, which is going to be negative 9.8 meters per second, and I'm going to multiply that, of course, times t squared. Now, in this next step, what I'm going to do is basically drop the units out and rearrange this equation just a little bit. I'm going to leave the 0 on the left, but I'm going to move this term over here over first, and I'm going to do that so that you can kind of recognize its form. I get negative 4.9 t squared, again I've left the units out on purpose, plus 39.1 times t, plus 125. Now take a look at what I've basically, what I'm going to box in here. What you're looking at right here should look familiar to you. If you attempt to solve that for t, you're going to run into some problems. I'm going to move some of these other questions just a little bit further out of the way. And what you should recognize is that this is a quadratic that's in the form that you should be familiar with, and that is going to be ax squared, where negative 4.9 is your a value, plus bx, where positive 39.1 is your value for b, plus c, where positive 125 is your value for c. So again, I'm just going to write kind of this standard form so you kind of recognize it. Ax squared plus bx plus c. And plugging these values into some sort of quad solve or some other form of quadratic equation solver, either built into your calculator or onto your computer. If you don't have this built into your calculator, and by that I mean a quadratic equation solver that'll deal with something like this, I strongly recommend that you just jump onto YouTube and get that onto your calculator. When I run that through quad solve, I get two different time roots. The first time root is negative 2.45 seconds, and the second time root is 10.4 seconds. I should see here that obviously what that's telling me is that if I go back in time here, that the location minus 2.44 seconds from when it was launched, meaning 2.45 seconds before it was launched, it was at the ground level. But clearly that's not a valid time going backwards in time, and so therefore the only valid route and the one that I'm going to move forward with is 10.4 seconds. So the answer to part A, determine the time taken to hit point P, is found in this way, 10.4 seconds. Okay, now moving on a little bit, I should recognize again here, I'm going to go ahead and move these things. The next question is determine the range of the projectile. Oops. And the range of the projectile can be found using the horizontal equations that we haven't written yet, but we had kind of made room for up at the top. And the horizontal equation is going to look something like this, where I have my x component of velocity is going to be equal to my horizontal displacement delta x over my time interval. Multiplying both sides by t, I'm going to get Vx times t is equal to my range. Substituting some values in now, my horizontal component of velocity, or 65 cosine 37, is 51.9 meters per second. Multiplying that by the time that I found in part A, 10.4 seconds, is going to yield a range of 541 meters. So that will be my answer for part B, which is what's the range of the projectile? The range of the projectile is 541 meters. The next question, part C, asks for the horizontal and vertical components of the velocity. In this particular, in this part of the problem, I need to be careful. The way that I've written it here, it says the horizontal vertical components of its velocity, but the book is specific. It says it says the horizontal vertical components of its velocity, but it means at point B, P, or when it lands. A couple of things. If I go back to the top of the page here, give me one sec. We should recognize that if I draw in some velocity vectors, and I draw the horizontal component of velocity as this green line, the horizontal component remains the same at different points throughout the flight. So I'm just showing you, picking kind of some random points. That horizontal velocity is unaffected by gravity. It's non-accelerated. So the 51.9 meters per second that it had here at the very beginning of the flight is going to be the same horizontal component of velocity just before it strikes the ground. However, that's not true for the vertical component of velocity. If I go ahead and sketch that in, we can see that it gets smaller. Right here at the very top of the projectile, the velocity, the vertical component of velocity right here is equal to 0. We've seen that in problem solving throughout the course. But then after that, we can see that the vertical component of velocity is small and negative, but increasing in magnitude as we go further and further down. So this kind of sketch answers the question ultimately later on down here that I need to answer, and that is how do I find the horizontal and vertical components of velocity? So as we said, the x component of velocity is still 51.9 meters per second, and we found that out earlier in the problem. It hasn't changed. So that's the horizontal component of velocity just before it hits the ground. The y component of velocity, though, we're going to have to use some equations to solve for. We don't know what it is at the end, but we do know the initial y component of velocity, or v initial y, is given to me as 39.1 meters per second. And I also know the acceleration. Of course, that's negative 9.8 meters per second. And I know the time of flight. The time of flight is equal to 10.4 seconds. So when I take a look at what I have and ultimately what I'm looking for, I'm looking for v final in the y direction. I have v initial acceleration in time. It looks like the second equation would be the best way to find the final y velocity. So I'll write that out. V final y is equal to v initial y plus acceleration times time. Substituting in my values for initial velocity, I'll get 39.1 meters per second. I'm going to add to it negative 9.8 meters per second times my time of 10.4 seconds. I should recognize that this term here is all going to be negative. So as soon as it gets larger than 39.1, this y piece becomes negative. And by the time I reach 10.4 seconds, that in fact has happened. And I get negative 63.1 meters per second is my final y component of velocity. So part C effectively has two answers. The first one is the x component of velocity is 51.9, the same that it was when it started, and the y component of velocity is negative 63.1 meters per second. Part D goes on to ask what can we say about the magnitude of the velocity. So in part D, we have both the x and the y pieces, and now we have to say, okay, what's the magnitude? And as we can see, question E is going to eventually ask the angle. If I were to go ahead and make a quick sketch of a coordinate axis, which I'll do over here on the left, and I were to draw in the components of the vector, we know that the y component we just found is this negative 63.1 in the downward direction, and that the x component is a positive 51.9, we should be able to recognize right away that our resultant is going to be in this fourth quadrant, and it's going to be found by the sum of the x and the y components. Now I can go ahead and label those if I want to. This is going to be my resultant, or basically what my velocity is. This is the x component of velocity, and this blue piece here is the y component of velocity. Now again, we've seen this in class. If I were to one way to consider this graphically is if I were to make a copy of this y component of velocity and move it over here, I now have the familiar right triangle. And I should recognize that since I know the blue side and the red side, I can find the unknown side by using the Pythagorean theorem, especially if I write in the kind of familiar math terms, a, b, and c. So I'm going to use the Pythagorean theorem. C squared is equal to a squared plus b squared. But substituting in some physics terms, I'm going to get my, basically, my resultant squared is going to be equal to side b, which we can call the y component of velocity squared, plus side a, which I can call the x component of my velocity squared. And so then finally we could say that my the magnitude of my velocity, which I'll kind of describe this way, is going to be the square root of vy squared plus vx squared. And we know that these values are have been solved for in the previous step. So we know that they're negative 63.1 meters per second, and that whole quantity is squared, and I'm going to add to it 51.9 meters per second, and I need to square that whole value. Let me go ahead and extend this. When I run that through my calculator, I should find that the magnitude here is going to be 81.7 meters per second. So the answer to part D, what's the magnitude of the velocity? 81.7 meters per second. Of course, we were well prepared to answer the next question. We knew it was coming. It usually is. And that is, what's the angle made by the velocity vector with the horizontal? Here's the angle theta that's in question. And I should recognize that the tangent is going to be the opposite side, or the y component, over the adjacent side, which is the x component of the vector. If I were to write that out, I would say then that tan theta is equal to opposite over adjacent. This is the TOA in SOHCAHTOA, if you will. Writing this in physics terms, the opposite side is the y component of the velocity over the x component of the velocity. So finally then, I can say that theta is the arctan, or the inverse tangent of that ratio, Vy over Vx. Plugging that into my calculator, I'm expecting a fourth quadrant vector. So if I don't get one, I'm going to be alarmed. Inverse tangent of my Vy, which is this value of negative 63.1 meters per second, and I'm going to divide that over 51.9 meters per second, which is my x component. When I run that through my calculator, I get negative 50.6 degrees, which is a fourth quadrant vector, and it is something on the order of what I expected. So the answer to part E is negative 50.6 degrees. All right, we're almost there. This has been a long one. The last question is find the maximum height above the top of the cliff. If I pan to the top of the page really quick, we'll see here that if I were to kind of draw a line on this page, on the plane of the top of the cliff, I should be able to see that this is the delta y that I'm looking for. So how far above the cliff did the projectile go? And you should recognize that when it reaches its maximum height, or I could say that the velocity final in the y direction at h max, and this is always true, is equal to 0 meters per second. We know the initial y component of velocity when it was fired. Of course, that is 39.1 meters per second. We solved for that earlier. We know the acceleration, it's negative 9.8 meters per second, and then finally we're looking for delta y in this case, or how high above that plane that it was fired. If you take a close look at these four variables, the third equation of kinematics is the best candidate to solve this unknown. I'm going to get Vf squared is equal to V initial squared plus 2a delta y. Solving for delta y, I get Vf squared minus Vo squared all over 2a is equal to delta y. Plugging in my values for V final is 0, V initial is 39.1 meters per second. I have to remember to square that. I'm going to divide this by 2 times negative 9.8 meters per second. Notice the negative in the denominator is going to cancel out with the negative in the numerator, and when I run that through, I get 78.1 meters is equal to my vertical displacement over the top of the cliff. So that finishes a lengthy problem, 31, which really takes a look at a lot of different aspects of the projectile portion of the kinematics chapter.